Welcome back. So let us have a recap of what we have done so far. So you consider any function, periodic function, essentially piecewise continuous periodic function, which you think of as a time signal, and it is a signal, and so it is a function of time, so you call it time signal. If it is a real valued function, so for example if you are just calculating, if you are measuring some voltage in some system, so it takes some real numbers, so between some finite, so some set of numbers. So you can put those numbers in some finite interval. You can think of a system repeats within this. So you can extend this function. So range of this function is actually that particular, it will be falling into that particular interval, and then so let us say its period is some L, and you can so beyond 0 to L and L to 2L and so on, you can go on extend the function as a real valued function over a full real line. So such a time signal you can always represent as a linear combination of signals of discrete frequencies. So this is we call Fourier series. So what we have done is so far is we defined Fourier coefficients. So based on so using these Fourier coefficients, you just take the linear combination with these fundamental functions, fundamental signals, or these discrete signals with discrete frequencies. You combine them and it will give you some series, function series, and the claim is that this function series is called Fourier series. This Fourier series converges pointwise to the original time signal. So this is that is where we just believe that it actually converges if it is a piecewise continuous function, and we just calculated with for two examples Fourier series. So if we look at this Fourier series, so for a function fx of period L, we have written like this: a naught by 2 plus sigma n is from 1 to infinity a n cos n omega naught x plus b n sin n omega naught x with omega naught as 2 pi by L, where so this is a Fourier series and these coefficients are 2 by L. Let us write a n's are same, so a n integral minus L by 2 to L by 2, and then you have this fx with cosine function dx, and b n's same thing with the sine function fx sin n omega naught x dx. So these are all running from n is from 0, 1, 2, 3 onwards. This is running from n is from 1 to 3 onwards. So this is not the only representation. So what we call this, these are Fourier coefficients. Fourier coefficients. This if you define like this if you take it as a definition, you take what you have is a function f, that is time signal, you can represent as a linear combination of a and b n's as coefficients, linear combination of these fundamental signals, okay, with discrete frequencies. Frequency is n omega naught. So this is equivalently you can put it as complex valued functions. These are all real valued functions, cosine function and sine function. These coefficients a n and b n, if you observe, these are all real functions, real constants, okay. So you can use cosine and sine, cosine function and sine function, if you write it as exponential functions by these you can use the Euler representation of a complex number, okay. So if cos theta plus I sin theta is, if you can write it as e power I theta, that is the Euler representation of a complex number. You can see that right hand side you can make everything in terms of exponential functions, and then coefficients will change accordingly. But the left hand side, if is the time signal which you started, if you are just measuring, it's a measured quantity is a real number, so it's a real quantity, real function, real valued function fx, and that is a signal. And we also mentioned that signal can be a complex quantity. So you can think of a repeated system. So just position of a vector, so position of a circular system. So, you can see that all the time that it rotates about certain origin. So, you can think of a system taking some following a circular path. If you take it as that way, r and theta. So, r is a function of, this is position vector x y, you can write it as a complex number z of t, which is x of t plus I y of t. So, this you can write it as r of t. Every time it can change, this need not be in the circular shape. Circular shape, if it is constant. For example, rotation of satellites, if you see path of the satellites, if you see, that is actually its elliptic path. So, whatever may be the shape, you can write it like this by Eulerian representation of a complex number, that is e power I some theta of t. Okay. So, something like this. So, theta is fixed. So, theta is between 0 to 2 pi. So, theta. So, if it has certain frequency, you can put it like omega. So, let us write. So, anyway, this is a complex number. So, this is e power I theta. Theta is between 0 to 2 pi. This is what you can write. So, you can see that if you are measuring the position of a satellite, then what you see is that this is a complex number. For every time, each time you have its amplitude and its what is its argument, e power I theta. Okay. So, this is a complex number. So, you can have, so what I mean to say is this, that a signal can be a complex valued function of time. So, if you have such a thing, it's natural to represent the right hand side as functions of complex as a complex valued function. Okay. Right hand side you can represent as a complex valued function. So, how do we do this? So, the best the way is cosine and sine function, you can think of n omega naught x, you can rewrite it as exponential. Once you know z is z of t is or rather cos theta plus I sin theta as e power I theta. So, this is what is the Euler representation of complex number cos theta plus I sin theta. So, if you use this one exponential, so cosine and sine is the sum of e power I n omega naught x plus e power minus I n omega naught x divided by 2. This is for cosine, and sin n omega naught x also you can write e power I n omega naught x minus e power minus I n omega naught x divided by 2i. If you write like this and use them in the Fourier series here, what you see is that it will become right hand side becomes complex valued functions in terms of complex valued functions. These are exponential functions. So, we will see, we will just replace cosine and sine there and see what happens to your signal. So, f of x, that is a function which is a0 by 2. As of now, I will just leave constants as it is plus sigma n is from 1 to infinity. You have a n as are constants. We will replace cosine with this exponential I n w naught x plus e power minus I n w naught x divided by 2 plus b n e power I n w naught x minus e power minus I n w naught x divided by 2i. So, if you simplify this, you take you can write a0 by 2 plus the sigma n is from 1 to infinity. You take simply what is the coefficient of e power I n w naught of x, that you collect it. So, you see that a n by 2 minus, so you can bring it bring this I up. So, you have a minus I times b n by 2, okay, plus e power, collect the coefficient of e power minus I n omega naught x, that will become a n by 2, and this minus minus plus here it becomes, you get I b n by 2. Okay, so, this is what you get. So, this is finally what you get is clearly you can see that B 0 equal to 0. If you actually see B n, put n equal to 0 because of sine function, it is 0. So, clearly B 0 is 0. Okay. See that B 0 is 0. So, if you add this A 0 plus B 0. Okay. So, you can write n equal to 0. So, you can write A 0 minus I B 0 by 2 is same as A 0 by B, A 0 by 2 plus this first part. So, you can this one combine this with this e power I n omega naught x A n minus I B n by 2 plus e power minus I n omega naught x A n plus I B n by 2. This is what for this full summation, and you can put this in terms in the first term. So, that will make it n is from 0 to infinity e power I n equal to 0 1. Once you put n equal to 0, I n omega naught is simply 1. So, that is 1 into A 0 minus I B n. So, I have added everything. So, A n minus I B n divided by 2. So, n is from 1 to infinity is this term, n equal to 0 term is this one, and you can also have n is from 1 to infinity, that is for the second term e power minus I n omega naught x A n plus I B n divided by 2. This is what you have. So, let us define. So, these constants as some Cn's. So, that these are your Fourier coefficients Cn, complex valued Fourier coefficients, and these are Cn's are A n minus I B n by 2 running from n is from 0, 1, 2, 3 and so on. Okay. So, and then what happens here? So, this is Cn is the coefficient of exponential e power I n omega naught x. Here this side, if that is the case, if you define like this, then C minus n will be here from the second sum. You can see that it is going to be A n plus I B n by 2. Okay. So, this is running from n is from, so this is how I defined Cn's, n is from 0 to infinity I defined as this one, this term, and this coefficient I define it as C minus n, which are running from 1 to 3 and so on. So, if you define like this, then what happens to your f of x? F of x will be, now you have the summation n is from 0 to infinity Cn e power I n omega naught x plus another sigma n is from 1 to infinity C minus n e power minus I n omega naught x. Okay. So, this is if you combine together. So, what you get is, so this you can rewrite. So, you can rewrite this as n is from 0 to infinity, this you as it is you write e power I n omega naught x. The other one you can change the index with n, replace you replace n by minus n. So, you get minus n equal to 1, that is same as n equal to minus 1 to infinity minus infinity, and you have a C n e power, the place of n I am putting minus n. So, you get this will become plus n I n omega naught x. Now, you can combine this together. So, you can write it, put it together. So, that is going to be from minus infinity to 1 minus 1 and then to 0 to infinity. So, finally, it is going to be minus infinity infinity C n e power I n omega naught x. This is what it has become, Fourier series has become now, okay, where the coefficients are A n plus, what is this? So, C n A n minus I B n by 2, A n minus I B n by 2. So, what is this A n B n? You already defined. So, if you replace, what happens to C n? C n's become A n is 2 by L. So, 1 by 2 times A n is 2 by L minus L by 2 to L by 2 f x cos n omega naught x dx then minus I, Bn is also, so 2 by L minus L by 2 to L by 2 Fx sin n omega naught x dx. So, this is what it has become Cn equal to, so 2 goes, and what you have is 1 by L comes out, this is from minus L by 2 to L by 2, Fx is common, you can combine these 2 together, Fx, what you have is cos n omega naught x minus I sin n omega naught x, this into dx, and this is nothing but 1 by L minus L by 2 to L by 2 Fx, and this is nothing but e power minus I n omega naught x dx. So, this is my coefficient it has become in terms of this fundamental function. Instead of writing cosines and sines separately, you put it together and write it as an exponential function. So, what you get is this one. So, this, if you say that this is your Fourier coefficient, this is your, if you say this is your definition of Fourier coefficient, what you get is the, in it, that your time signal, you can write it as, this is your Fourier series. A Fourier series has become a complex Fourier series. Okay. So, if you have a time signal that is a complex valued, so you can represent, you can always represent this way. Okay. It makes sense to represent as a complex Fourier series. So, with this definition as your Fourier coefficient, this is easy to remember. Okay. So, and you can put it this way. So, this is in a better form than the Fourier coefficients in terms of cosines and sines, and then writing that Fourier series, okay, in terms of them. This looks much compact and it's a nice form. So, it's natural that a signal can be, a complex signal. In that case, you have a complex Fourier series. That means a signal, complex signal, you are writing as a linear combination of all these fundamental complex signals of discrete frequencies. Those are exponential functions e power I n omega naught x. So, this is how you get this Fourier series. So, as of so far, this is still have not answered the question that this, whether this series is converging to Fx or not. So, you are only believing that. So, you define this as a Fourier coefficient, you get a Fourier series. This is actually, so we have not done anything new so far. So, we just combined this Ans and Bns together and put it as a complex Fourier series. So, the signal you are writing as a Fourier series, it actually again if your signal, complex signal is piecewise continuous function, you can still believe that this Fourier series based on the Cns and exponential functions, put it together, that series converges, the complex number series converges to the signal, time signal Fx at x. Once you fix x, that is what it happens. So, you can say we will prove that eventually. So, this is your actually crux of the Fourier series. What to calculate the Fourier series, you just have to define your Fourier coefficients and calculate the Fourier series. So, but then you have to remember every time your what is your cosine function. So, where is these cosine functions are coming from? Cos n omega naught x and sin n omega naught x. When you have the fundamental frequency is 2 pi by L, that means your signal is of time signal with period L. You have this is your fundamental frequency, these are your fundamental signals, and you just have to remember these Fourier coefficients A n, which you define as a sum integrals, A n's and B n's. So, where are they coming from? They actually, if you know the differential equations, they are actually coming from differential equation. So, some particular differential equation. So, that is a Sturm-Liouville problem. You can get all these as a solutions of a Sturm-Liouville system. So, eigenvalues which are non-zero solutions of a Sturm-Liouville system, that is where and you can see that these cosine functions, sine functions are actually coming from a differential solution of a differential equation. So, if you know the differential equation, if you have done the earlier course differential equations for engineers, so you can see that we have done Sturm-Liouville system. If I write like this y double dash plus a lambda y equal to 0. So, this is in the self adjoint form, that is p equal to 1, p of x equal to 1 into y, for which you have a derivative y dash and you have a derivative, that is nothing but y double dash, okay, plus q is q okay, plus lambda times omega is 1, omega of x is 1, that is a weight function, and y equal to 0. So, this is your differential equation. Y is a function of x. So, x is between 0 to L, if you define it like this. And what happens to if it is a periodic Sturm Liouville system? Periodic Sturm Liouville system. If you know the differential equations, you just understand this, otherwise you do not need. Okay? So, you just have to remember these cosines and sines. And this is your Sturm Liouville form. So, the self adjoint form, your differential equation is in self adjoint form with the boundary conditions. The domain is 0 to L, and you have to give the boundary conditions. Those are periodic boundary, because it is a periodic Sturm Liouville system. Lambda is the parameter. So, lambda is a parameter. If it is a self adjoint form, lambda is always real. So, it is a real parameter because it is in the self adjoint form. And once you see this is a self adjoint form, the dot product between the solutions, always you have to identify that is always in this form. So, integral is between 0 to L, that is the domain, and fx gx into wx. The wx is a weight function, that is 1. So, you have a usual dot product. So, this is the dot product with respect to which the solutions of these will satisfy, they are actually form complete orthogonal set. That orthogonal means a complete set of functions. Any function you can represent in terms of the solutions of this with respect to this dot product. So, let us see the boundary conditions. So, boundary conditions what we give in this periodic system is y at 0 is same as y at L, and y dash at 0 is same as y dash at L. So, if you take this as a boundary conditions, and this is your equation, if you solve it, solutions are if you see, if you actually solve this for different because it is a real parameter, is a real parameter because it is in the self adjoint form. Lambda can be positive, lambda can be negative, and lambda equal to 0. In all cases, if you calculate, what you see is these are cos. So, what are the solutions? So, let me put these solutions in a different form. So, what I do is, because we have not taken the period 0 to, we have taken the period L, but our domain is not 0 to L. Earlier when we have the Fourier series, we have taken from minus L by 2 to L by 2. So, here also let me take that way. So, that your integral will be from minus L by 2 to L by 2. This is the dot product between the functions, which are the solutions of this equation satisfying this boundary condition. So, 0 y L by 2 rather. So, minus L by 2 to L by 2, and here minus L by 2 y derivative is also will have plus L by 2. So, these are your boundary conditions. So, periodic boundary conditions. Now, your domain only we have changed. So, what are the solutions here? So, if you have such a thing, your solutions will be if you actually see that. So, the solutions are non-zero solutions. Non-zero solutions will be, if you actually see, they are cos n 2 pi by L x and sin n 2 pi by L into x. So, n is running from 0, 1, 2, 3 and so on. This is what you will see. Okay. If you just go through how to if you just find this solutions of this periodic Sturm Liouville system, you will see that these are your solutions. These are exactly our cos n omega naught fundamental frequency x and sin n omega naught x. So, n is from 0, 1, 2, 3 onwards. So, for n for cosine function, this is anyway n is running from 0 to, for sine function when you put n equal to 0, that is anyway 0. So, you are looking for non-zero solution, that does not count. Okay. So, you say it is from 1, so you have to 1 cos n equal to 0, that is 1. So, you say these are your solutions, non-zero solutions. So, in terms of these are your fundamental signals, in terms of this you are writing piecewise continuous function, you are writing in terms of these fundamental functions. Okay. So, that is how these cosine functions and sine functions are coming into your Fourier series. Okay. So, actually what is giving is a Sturm Liouville system with periodic boundary conditions is giving you the actual Fourier series. If you change this differential equation, you may get a different Fourier series. Okay. So, it depends on so if you want to remember this cosine sine function with exact this fundamental frequency, you just write this y double dash plus lambda some parameter into y. So, this one equal to 0 over the domain over the time over the domain of the time signal, that is minus L by 2 to L by 2, and then you have you give the boundary conditions at the endpoints as always like this. Endpoint at minus L by 2 is one endpoint. A value of the function y at that point should be same as value at L by 2 because it is repeating, it is a periodic, and its derivative also should satisfy the same conditions. So, if you give this, you will get what you want, those fundamental solutions. The solutions of the system is actually those fundamental solutions. They are actually orthogonal. So, with respect to this dot product, they are all actually orthogonal. That means integral minus L by 2 to L by 2, instead of f and g you give cosine and sine. If you give anything different from this, that is cos n omega naught x into sin n omega naught x dx is always 0, okay, for every n equal to 0 anyway it is true. So, this is true, and if you calculate L by 2 to L by 2, same function, for example cos square itself you take cos square n omega naught x dx, this will give me what is this value. So, 1 plus cos 2 n omega naught x divided by 2, so that will give you so L by 2. Okay. So, that will give you L by 2. So, this is the number which is showing up in your coefficients a and bn. A and bn you have this coefficient, that is integral. So, 2 by L times minus L by 2 to L by 2 fx cos and sine both n omega naught x dx. Okay. So, this is actually both these together. So, a and bn can be represented this way. One is a n for cosine you consider for a n's and sine you consider for b n's. So, where is this L by 2? So, this over minus L by 2 to L by 2 cos square n omega naught x or sine square n omega naught, that is dx, that value is actually L by 2. So, that is what you will see, you are seeing here. Okay. So, either this cos square or sine square. So, together you will have only the same value, and if it is n, so if you simply take this 1, even that includes n equal to 0, also n equal to 0 you have this function constant function 1, for which if you take this limit dot product itself, that value is actually L by 2. So, it is valid from n is from 0, 1, 2, 3 onwards. So, this is how you get these cosine functions, sine functions. Same way you can see, so if you combine them, what you are seeing is this complex Fourier series anyway. Okay. So, complex thing you do not get it from the Sturm Liouville system, and this is how you get these fundamental signals cos n omega naught x and sin n omega naught x. So, given a time signal you need not represent always in terms of cosine and sine functions. Okay. So, you consider some Sturm Liouville differential equation with the periodic boundary conditions, you may end up different solutions, non-zero solutions. They are linearly independent solutions and they form complete orthogonal set. So, that complete orthogonal you can get it from here. So, this is, that means they are actually perpendicular to each other. If you take any two different fundamental functions, they are always orthogonal, that means their dot product is 0, and if and also they form complete set. Complete means complete set means any signal f of x, every function f of x I can represent in terms of these functions. So, that is exactly your Fourier series, that is start with a0 some arbitrary constant with this 1 plus sigma n is from 1 to infinity. So, you can write a n cos n omega naught x plus b n sin n omega naught x dx. Yeah, this is your complete set. That means any function f, any signal I can write in terms of these complete set. That is exactly our Fourier series. A naught is a naught b naught a, where a n, where a naught is equal to. So, how do you get this a naught? So, a naught, if you have this represent complete set means this. What is this a naught? A naught is actually, you take a dot product with both sides with a naught to a naught, the dot product both sides, and because they are orthogonal, this other everything else will go, only this right hand side you have this, left hand side you have fx dot product with a naught. So, what is this one? This is same as, so you have a naught. So, dot product is L by 2, a naught just comes out. Okay. So, what is this one? This is actually minus L by 2 to L by 2, a naught square dx, right. It is not a naught square dx, yeah, that is true. Or you just take the dot product with fundamental function. So, that is 1. So, you have only a naught dx, this is equal to a naught L by 2, which is equal to minus L by 2 to L by 2 fx a naught dx. So, what is this one? So, a naught goes, what you have left with is so I have taken a naught as 1. So, you have this, there is no a naught here now. So, this will give me a naught, the constant, arbitrary constant as 2 by L minus L by 2 to L by 2 fx dx. So, instead of 1, if you take the dot product with fx times cos n omega naught x, if you take the dot product. So, first term a naught cos n omega naught x, that is 1 a naught into the dot product with cosine, that is 0. So, what you have the right hand side only a naught will contribution will be there. So, you get a naught dot product with cos, or rather a n, only a n will be there. So, a n cos n omega naught x dot product with cos n omega naught x. This symbol represents the dot product which you should recognize from as soon as you have this sturm Liouville system. Okay. So, this is exactly L by 2 a n, we have seen already this dot product. So, that is again, so you see that a n equal to 2 by L integral minus L by 2 to L by 2 fx cos n omega naught x dx. These are exactly your Fourier coefficients a n, and similarly you can do, if you consider dot product with sines, you have what you get is b n's, instead of a n's you get b n's, and here instead of cosines you write sines, okay, and what you end up is L by 2 b n. So, you get b n as again 2 by L minus L by 2 to L by 2 fx sin n omega naught x dx. So, these are exactly your Fourier coefficients. Okay. So, you change this differential equation, this periodic sturm Liouville system with each time you change the differential equation, you may end up these non-zero solutions, they form complete orthogonal, this gives you orthogonal complete sets, that is exactly your Fourier series. Okay. So, you will have a different representation, but every time you will have only discrete number of such functions, solutions are only discrete such functions. So, that means every signal you need not represent in terms of discrete signals in terms of cosines and sines, it can be different functions, okay, but they are all discrete, countable number of solutions, fundamental solutions. Okay. So, that is how you get this Fourier series. So we have not only this a and b n, we have seen that this in terms of complex numbers, complex Fourier series you have seen. So now we are in a position to see, we will just take up some other example. We will take some example and try to give you try to represent that in the complex Fourier series. For example, the one we have done. So let us do some example. You consider the function f(x) which is mod x. Well, let us take only a real valued function. Okay. Still you can represent in terms of exponential function. Complex Fourier series you have seen what this as in terms of a and b n's, the real Fourier series you have seen. Now we can write in terms of complex Fourier series, that is between 0 to, let us take between x to x is between 0 to L. Okay. So how does this look? This looks like 0 minus so let us say 0 to L, and this looks like, so let us do it from minus L by 2 to L by 2. Then how does this look? L by 2 to L by 2, this is the period of period L, this is a function with the period L. So you have, this is always positive, so this looks like V shape, and you extend it over L 3 by 2. So again it looks like this is your L and this looks a V. Like this you can go on extend it as periodic function or full real line. So if you take this one, a n's b n's you have calculated. Now your Cn is Fourier coefficients are Fourier coefficient, complex Fourier coefficients you can calculate now. Cn's both are same. Okay. So you have Cn's, what is your Cn? You have, so the period is L, okay, and the fundamental frequency is the omega naught, which is equal to 2 pi by the period L, that is what it is. So you have Cn is 1 by L minus L by 2 to L by 2. So f(x) e power minus I n omega naught is 2 pi by Lx dx. So let us calculate for this and see what it is. So 1 by L minus L by 2 to L by 2, f(x) is, when it is negative side, minus L by 2 to 0. So this is simply minus x. So you have minus x e power minus I n 2 pi by Lx dx, and plus 1 by L over a different domain 0 to L by 2, mod x will be simply x e power minus I n 2 pi by L x dx. You call this, you work with as W naught, that is better. So for simplicity you can do that, and now you can see you can represent minus 1 by L, put x equal to minus x. If you do that, minus plus x minus x, and dx is minus dx, that is minus plus, and this will become L by 2 to 0, and then this will become e power I n omega naught x dx, right. So it is this minus will become 0 to L by 2, remove this. So this one plus 1 by L 0 to L by 2, of course x is there, and x into e power minus I n omega naught x dx. So you see that both are same. So you get 1 by L. So actually this is sum of the, if you combine them together, this is actually 2 by L integral 0 to L by 2 x cos n omega naught x dx. So this you can do because it is a sum, you can calculate this Cn. Okay. So here you do not have to do for separately for a n and b n. So you have, this is running from minus infinity to infinity. So this is like saying 0 plus or minus 1 plus or minus 2 and so on. So like this you can put. So you are actually calculating for every n. So now this you can do the integration by parts, 2 by L So, if you do the 2 by L integration by parts, sin n omega naught x divided by n omega naught. So, the derivative is this x, now you apply these limits, minus 2 by L into n omega naught integral 0 to L by 2, and you simply have sin n omega naught x into the derivative of x is 1. So, you have dx. So, in this one n omega naught is n into 2 pi by L. So, L by 2 when you substitute is n pi, that is 0, and when you put n x equal to 0, this is anyway 0. So, contribution is nil here. So, you are left with minus 2 by L into, so n 2 pi by L. So, 2 pi n, so simply pi n 2 goes here, L n omega naught, that is L n 2 pi by L. So, 2 n pi. So, divide by 2 n pi, this 2 goes numerator denominator. So, this will be minus minus plus cos n omega naught x by n omega naught. This is running from L by 2. So, this is, what is this value? So, finally, n omega naught is nothing but n 2 pi by L, right. So, you have 2 by L this, and you have this, yeah. N omega naught is n L divided by n square pi square by 2, right. So, what is this n omega naught? So, n omega naught is this one. So, 2 n pi by L, 2 n pi by L. So, L by 2 n pi. So, this is what it is, and if you apply this cos limits, cos n 2 pi by L into L by 2, 2 goes. So, cos n pi minus cos 0, that is 1. So, this is what it is. So, you have L divided by 2 n square pi square, and here cos n pi is minus 1 power n minus 1. This is exactly, because you see that it has to be real valued Cn's, because f is a function and everything has to be real valued. So, Cn's are real. So, you get it as this function Cn's are real. So, this implies that function mod x in the interval minus L by 2 to L by 2, this function mod x, you can write it like, so linear combination n is from minus infinity to infinity, this Cn, that is L by 2 n square pi square minus 1 power n minus 1 times e power minus, this is now plus. What is your Fourier series? Fourier series, complex Fourier series, you can see that it's going to be with plus sign. So, you see that this is your Fourier series, complex Fourier series with plus sign, e power I n omega naught x, e power I n omega naught, n omega naught is 2 pi by L x. This is exactly, x is between minus L by 2 to L by 2. So, this is the Fourier series for the time signal mod x, whose period is L. Okay. Still, this convergence of this complex numbers, this complex number series, whether it converges to mod x once you fix x, still questionable. So, this is what exactly we will see in the next video. We will try to develop relevant things we will do, and then we will try to prove the Fourier series of a time signal converges to the time signal at some particular time always, whenever there is the minimal condition is f is piecewise smooth function or piecewise differentiable function. Okay. It is also true. So, that means there are sufficient conditions. If a time signal is piecewise differentiable function, I can immediately easily prove that this Fourier series converges to the time signal, the function f x. Okay. We will see in the next video. Thank you very much.